Hi everyone, I'm John from ProDake Labs and this is session number 7, Static Structural Analysis. This video will teach you all you need to know to perform static structural analysis using Ansys Workbench. So, let's get started. What is static structural analysis? Static structural analysis determines the displacements, stresses, strains, and forces in structures or components caused by loads that do not induce significant inertia and damping effects. Steady loading and response conditions are assumed. That is, the loads and the structure's responses are assumed to vary slowly with respect to time. A static structural load can be performed using the Ansys. The types of loading that can be applied in a static analysis include externally applied forces and pressures, steady-state inertial forces such as gravity or rotational velocity, imposed displacements, temperatures for thermal strain. Let me explain this with the help of an example. After completing this session, you will be able to create the static structural analysis system, apply boundary conditions, apply different types of constraints, apply different loads available in Ansys Workbench, generate the result of an analysis, generate report of an analysis. So, let's get started. In this session, we will create the model of a cantilever beam with the dimensions of 12 mm thickness, 50 mm width, and 300 mm length. After creating the model, we need to run a static structural analysis on the model and evaluate the total deformation and the directional deformation. Determine directional deformation along the X, Y, and Z axis. After evaluating the results, interpret them. To start a new static structural analysis system.
Thank you, John, for precisely defining static structural analysis. As a first step, we'll start new project in Workbench window. Now click on OK button to proceed and save the project in your preferred location. Name the project AS001 and click on Save button. Next, drag the static structural analysis system from the Analysis System drop-down menu and drop it into the project schematic window. Next, rename the system as Simply Supported Cantilever Beam. Now, we need to create a cantilever beam model as per given dimensions. To do so, double-click on Geometry. The Designer Modeler window is opened. Choose Millimeter from the Ansys Workbench window. Next, select XY plane from the tree outline. You need to orient the plane normal to the viewing direction, so select Look At tool from the toolbar. Now, select the Sketching tab and select Rectangular tool from the Draw toolbox. Then, draw a rectangular sketch and press Escape button to exit from sketch mode. Next, assign the dimension to the sketch as per drawing. Next, we need to extrude the sketch. To do so, select Extrude tool. Enter the beam length 300 mm in the FD1 Depth Edit box under the Details View window. Then, click on Generate tool. Now the cantilever beam part is created. Next, we need to generate a mesh on created model. Close the Design Modeler window now. After the model is created in the Design Modeler window, you need to generate the mesh for the model in the mechanical window. Double-click on the model cell in the simply supported cantilever beam analysis system. The mechanical window is displayed. Right-click on the mesh in the tree outline and select the option Generate Mesh. Expand the Statistics node in the Details of Mesh window to display the total number of elements created. On doing so, you will find that the total number of elements created is 80.
After the mesh is generated, you need to set the boundary and loading conditions under which the analysis will be performed.
Select the Static Structural node in the tree outline. The Details of Static Structural window is displayed. Also, the Environmental Contextual toolbar is displayed. In the Environmental Contextual toolbar, choose the Fixed Support tool from the Supports drop-down. Fixed Support is attached to the tree outline. Also, the Details of Fixed Support window is displayed. Next, select the face of the model. The face turns green. Click on the Apply button in the Geometry selection box to confirm the selection of the face is Fixed Support. The color of the face turns violet and a flag is attached to the face. After the boundary is defined for the model, you need to define the load for which the analysis is to be carried out. Select the Static Structural node in the tree outline to display the Environment Contextual toolbar. In the Environment Contextual toolbar, choose the Force tool from the Loads drop-down. Force is attached under the Static Structural node in the tree outline. Also, the Details of Force window is displayed. Force is known as the rate of change of momentum. In Ansys Workbench, you can apply force load by choosing the Force tool from the Loads drop-down. Now, we need to select edge in the model, but I'm unable to select edge because Edge tool is not selected. Choose the Edge tool from the Select toolbar to select an edge from the graphics screen. In the graphics screen, select the edge just opposite to the face on which you have applied the Fixed Support. Choose the Apply button. The edge is selected for applying the force load. Next, select the Magnitude Edit box and then enter 500 as the magnitude of force load. The Magnitude Edit box is used to specify the magnitude for a vector quantity. Select the Direction selection box to display the Apply and Cancel buttons. Next, select the vertical edge of the model. The Direction selection box is used to specify the direction of a vector quantity. You can also flip the arrow to change the load direction by using Flip Toggle button. Choose the Apply button in the Direction selection box. Now, pre-processing part is complete. Next, you need to work on the solution part of the analysis.
After the boundary and loading conditions are specified for the analysis, you need to evaluate the results that are of importance in the case of a particular analysis. You can view the response of the model under given boundary and loading conditions. The various results that can be evaluated are deformation, stress, strain, energy, and linearized stress. To evaluate the results in this analysis, follow the procedure explained next.
Select the solution in the tree outline. The Solution Contextual toolbar is displayed. Also, the Details of Solution window is displayed. Choose the option Total from the Deformation drop-down in the Solution contextual toolbar. Total deformation gets attached under the Solution node. Also, the details of Total deformation window is displayed. Next, choose the option Directional from the Deformation drop-down. Directional deformation is attached to the tree outline. Also, the details of Directional deformation window is displayed. A body is called to be deformed if its shape is changed temporarily or permanently. The temporary change of shape is known as elastic deformation, and a permanent change of shape is known as plastic deformation. In Ansys Workbench, you can determine deformation in terms of total and directional deformations. Total deformation is the total change of shape in a given working condition. You can view the total deformation induced in any component by using the Total tool from the Deformation drop-down in the Solution contextual toolbar. Directional deformation is the total change of shape in the particular axis due to given working conditions. You can view directional deformation by using the Directional tool from the Deformation drop-down in the Solution contextual toolbar. Total deformation is the summation of all directional deformations produced in a certain region of the model. If deformation in x-axis is ux, deformation in y-axis is uy, deformation in z-axis is uz, then the equation describing the total deformation is u is equals to square root of ux square plus uy square plus uz square. In the Details of Directional Deformation window, expand the Definition node if it is not already expanded. Notice that in the Orientation drop-down list, the default selection is X-axis, which means the directional deformation shown in the graphics screen is only with respect to X-axis. In finite element modeling, where the processing period is small, you can view the directional deformation with respect to the Y and Z axis in the same mechanical window. Next, select the Y-axis from the Orientation drop-down list. Next, click on the Solve tool from the Standard toolbar. The directional deformation with respect to the Y-axis is displayed in the graphics screen. Now, the directional deformation is done with respect to Y-axis. You can see the results of directional deformation along the Y-axis. You can also check the deformation by playing animation. Again, select X-axis from the Orientation drop-down list to evaluate the directional deformation with respect to the Y-axis only. After that, click on the Solve tool. Now, the X-axis results are appeared on the screen. You can play animation and check the deformation values. Now, if you again have to view the result of the directional deformation along with Y-axis, you have to repeat all steps again. This would result in more processing time as taken earlier. Therefore, it is recommended to create a duplicate of existing system so that you can view the result again and again at any time without repeating the steps. If you want to check the total deformation or directional deformation values, then click on Particular Deformation option in the tree outline, and the corresponding results will appear on the graphical screen. After evaluating the results, we will learn duplicating the system. To do so, switch from the mechanical window to workbench window. In the project schematic window, right-click on static structural. A shortcut menu is displayed. Choose the duplicate option from the shortcut menu. The copy of simply supported cantilever beam analysis system is created in the project schematic window. Next, rename the system as simply supported cantilever beam 2. Next, double-click on the model cell of the system B. Another mechanical window is opened. In the mechanical window, select Directional Deformation from the tree outline to view the details of Directional Deformation window. Next, select Y-axis from the Orientation drop-down list. Click on the Solve tool in the standard toolbar to solve the analysis for the directional deformation along the Y-axis. And you can see that the green tick mark is placed before the components under the solution node in the tree outline, indicating that all results are evaluated. Now the directional deformation is set along with Y-axis. Now you can close the mechanical window. Now you have two separate windows to analyze directional deformation along the X-axis and directional deformation along Y-axis. Similarly, you can create the copy of the existing analysis system and analyze the data with respect to Z-axis. As discussed earlier, it is convenient to analyze results in separate windows. Therefore, in case of large finite element models, you can validate data for different combinations by opening a new window using the duplicate tool. In project schematic window, displaying three analysis systems wherein cantilever 2 and cantilever 3 analysis systems have been duplicated from the cantilever analysis system. Note that cantilever 2 and cantilever 3 analysis systems are used to determine directional deformations along the Y and Z axis. Similarly, we need to create Z-axis by duplicating one more system in the project schematic window. System C is added in the project schematic window. Next, rename the system as simply supported cantilever beam 3. Next, double-click on the model cell of the system C. Another mechanical window is opened. Again, select the directional deformation from the tree outline to view details window. Next, select Z-axis from the orientation drop-down list. Click on the Solve tool button from the standard toolbar to solve the analysis for the directional deformation along the Z-axis. After the analysis is finished, the next important step is to understand the evaluated results. In this session, you have evaluated deformation so far. Now, it is required to check if the evaluated results fall under the permissible limit or not. To do that, select Total Deformation under the Solution node in the tree outline. The total deformation of the simply supported cantilever beam 3 is displayed in the graphics screen. Also, the corresponding legend is displayed in the graphics screen. The legend has colors arranged in a band from top to bottom. Depending upon the type of analysis and the parameters evaluated, each color will indicate a different value. The typical legend displayed when total deformation is selected from the tree outline. The blue color in legend indicates the minimum value of total deformation. If it displays 0, which means there is no deformation in that region. The value that is displayed next to each color is the total deformation in the region which is depicted by that particular color in the model. The red color denotes the maximum value of the total deformation. Right-click on the graphics screen and then select Choose View option and go to Right from the shortcut menu displayed to orient the model. Select the Show Undeformed Wireframe option from the Edges drop-down list in the Result contextual toolbar to visualize the extent of deformed shape. The undeformed wireframe model is displayed along with the deformed model in the graphics screen. Similarly, to show the elements that are created after meshing in the deformed shape of the model, select the Show Element option from the Edges drop-down list. Now you can see the elements on the model in the graphics screen window. To view the transparent mode, select the Show Undeformed Model option from the Edges drop-down list.
After you have evaluated all the results, you need to save the file before you exit the Ansys Workbench session. Thanks for tuning in and have a great day.